Your teacher today is Dr. Bosa, Science. Dr. Bosa is a teacher at the Science Foundation College, the best school that teaches sciences. Today we are going to study A-level Modern Physics, Lesson 1, Photoelectric Effect. Photoelectric effect is the emission of electrons from a material caused by light or electromagnetic radiations. In metals, atoms exist as positive ions in a sea of electrons. An electron near the surface of a metal, such as electron A, experiences an attractive inward force from the positive charges below it. For such an electron to escape from the metal surface, a specific amount of work or energy is required to overcome these inward forces. Terminologies. 1. Photoelectric emission is the liberation of electrons from a metal surface caused by light of a suitable frequency. That is, light or radiation supplies an electron with the amount of energy equal to or exceeding the energy that binds electrons to the surface. Semionic emission is the liberation of electrons from a metal surface by application of heat. Photoelectrons are electrons liberated by light striking a metal surface. Photoemissive surfaces are metal surfaces that emit electrons when struck by light. Potassium, sodium, calcium, and other elements with low ionization energy or work functions have surfaces that are photoemissive. Work function is the minimum energy required to liberate an electron from a metal surface. Each element is characterized by a specific value of work function. Laws of photoelectric emission. The laws or characteristics or features of photoelectric emission are a summary of experimental results on photoelectric effect. 1. The time lag between irradiation of the metal surface and emission of electrons by the metal surface is negligible. For a given metal surface, there is a minimum value of frequency of radiation called threshold frequency F0, below which no photoelectrons are emitted, however intense the incident radiation may be. The number of photoelectrons emitted from the surface per second is directly proportional to the intensity of the incident radiation for a particular incident frequency. 4. The kinetic energy of photoelectrons emitted is directly proportional to the frequency of radiation but independent of the intensity of the radiation. experiment to demonstrate photoelectric effect. The setup is shown below. A freshly cleaned zinc plate is connected to the cap of a negatively charged gold leaf electroscope, and ultraviolet radiations are allowed to fall on the zinc plate. Observations. The leaf of the electroscope gradually falls. This shows that both the zinc plate and the electroscope have lost charges. The lost charges are found to be electrons. Hence, photoelectric effect has occurred. Note that if a positively charged electroscope is used instead, there is no observable change in the divergence of the leaf, because the emitted electrons are immediately attracted back by the positive charges on the cap of the electroscope, and hence restoring the charges. Planck's quantum theory states that the energy or radiation emitted or absorbed by an electron is discrete or is in packets called quanta. That is, we can have integral values such as 1, 2, 3 to n, but no fraction amount of energy. The energy E contained in a quantum of a radiation is proportional to the frequency f of the radiation. That is, E is proportional to f, or E is equal to hf, where h is Planck's constant, equal to 6.626 times 10 to the power negative 34 joules seconds. For an electromagnetic radiation of wavelength lambda, we have C equal to lambda f, where C is the speed of light. It implies that E is equal to hc over lambda. Thus, E is proportional to 1 over lambda. When a photon collides with an electron, it is either A, reflected with no change in its energy, or absorbed by an electron, and this photon gives up all its energy to a single electron. If the energy E is greater than the work function W naught of the metal, the excess energy HF minus W naught is absorbed as the kinetic energy of the photoelectron. The photoelectric equation is given by HF minus W naught is equal to a half mv squared, where v is the velocity of the emitted electron, or HF is equal to W naught plus a half mv squared. Since the work function W naught is constant for a particular material, then W naught is equal to HF naught, where F naught is the threshold frequency. From HF minus W naught is equal to a half mv squared, then H into F minus F naught is equal to a half mv squared. Also, W naught is equal to HF naught, and F naught is equal to C over lambda naught. Then W naught is equal to HC over lambda naught, where lambda naught is the maximum wavelength of light that can emit an electron from a metal surface. If an electron of charge E is accelerated by a voltage V volts, it gains kinetic energy Ke equal to EV. Hence, from above, H into F minus F naught is equal to EV. Definition is an electron volt EV is the kinetic energy gained by an electron which has been accelerated through a PD of 1 volt. 1 EV is equal to 1.6 times 10 to the power negative 19 joules. Threshold wavelength lambda naught is the maximum wavelength of an incident radiation above which photoelectric emission cannot occur. Threshold frequency F naught is the minimum frequency of the incident radiation below which photoelectric emission cannot occur. Example 1. A monochromatic radiation of frequency 1.0 times 10 to the power 15 Hz is incident on a clean magnesium surface, for which the work function is 0.59 times 10 to the power negative 18 joules. Calculate 1. The maximum kinetic energy of the emitted electron is. Solution. Kinetic energy is equal to HF minus W naught is equal to 1 times 10 to the power 15 times 6.63 times 10 to the power negative 34 minus 0.59 times 10 to the power negative 18 joules, which is equal to 7.4 times 10 to the power negative 20 joules. 2. The potential to which the magnesium surface must be raised to prevent the escape of electrons. The potential energy is equal to kinetic energy. EV is equal to 7.4 times 10 to the power negative 20 joules. V is equal to 7.4 times 10 to the power negative 20 over 1.6 times 10 to the power negative 19, which is equal to 0.46 V. 3. The cutoff wavelength from W naught is equal to HC over lambda naught. Lambda naught is equal to 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 over 0.59 times 10 to the power negative 18. This is equal to 3.38 times 10 to the power negative 7 meters. Example 2. Calcium has a work function of 2.7 eV. A. What is the work function of calcium in joule? 1 eV is equal to 1.6 times 10 to the power negative 19 joules. Therefore, 2.7 eV is equal to 2.7 times 1.6 times 10 to the power negative 19 equal to 4.3 times 10 to the power negative 19 joules. B. What is the threshold frequency of calcium? HF naught is equal to 2.7 eV is equal to 4.3 times 10 to the power negative 19. Therefore, F naught is equal to 4.3 times 10 to the power negative 19 divided by 6.63 times 10 to the power negative 34. This is equal to 6.5 times 10 to the power 14 Hertz. C. What is the maximum wavelength that will cause emission from calcium metal? Lambda naught is equal to C over F naught. This is equal to 3 times 10 to the power 8 over 6.5 times 10 to the power 14. This is equal to 4.6 times 10 to the power negative 7 meters. Example 3. Light of frequency 6 times 10 to the power 14 Hertz is incident on a metal surface, and the emitted electrons have kinetic energy of 2 times 10 to the power negative 29 joules. Calculate 1. Work function. Solution. From HF is equal to W naught plus a half mv squared. W naught is equal to 6.63 times 10 to the power negative 34 times 6 times 10 to the power 14 minus 2 times 10 to the power negative 29. This is equal to 3.978 times 10 to the power negative 19 joules. 2. Threshold frequency of the metal. From W naught is equal to HF naught. F naught is equal to 3.978 times 10 to the power negative 19 divided by 6.63 times 10 to the power negative 34. This is equal to 6 times 10 to power 14 Hertz. Example 4. Calculate the maximum speed of photoelectrons emitted by cesium surface when irradiated with light of wavelength 484 millimeters if the work function of cesium is 3 times 10 to the power negative 19 joules. Given that the speed of light C is equal to 3 times 10 to the power 8 meters per second, H is equal to 6.63 times 10 to the power negative 34 joule second, and the mass of an electron, Me, is equal to 9.1 times 10 to the power negative 31 kilograms. From HF is equal to W naught plus a half mv squared, HC over lambda is equal to W naught plus a half mv squared. 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 over 484 times 10 to the power negative 3 is equal to 3 times 10 to the power negative 19 plus a half times 9.1 times 10 to the power negative 31 times V squared. Simplifying, V is equal to 4.938 times 10 to the power 5 meters per second. Example 5. A photoemissive metal has a threshold wavelength of 0.45 micrometers. Calculate the kinetic energy of emitted electrons when light of wavelength 0.35 micrometers falls on this metal. Given that C is equal to 3 times 10 to the power 8 meters per second and H is equal to 6.63 times 10 to the power negative 34 joules seconds. From HC over lambda is equal to HC over lambda naught plus kinetic energy. Kinetic energy is equal to 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 over 0.35 times 10 to the power negative 6 minus 6.63 times 10 to the power negative 34 times 3 times 10 to the power 8 over 0.45 times 10 to the power negative 6. This is equal to 1.263 times 10 to the power negative 19 joules.